In this video, we will be looking at rate of change. And before we get into the grade 12 version of rate of change, where we look at average rate of change versus instantaneous rate of change, we're going to do a little bit of grade 9 review by finding the slope of each of the following line segments. So I'm going to start with this first one here. I'm just going to zoom in a little bit. And we know to find the slope, we're going to do rise over run or y2 minus y1 over x2 minus x1. But because I have a nice little sketch here, I'm just going to pick 2 points that I can read off, and I see that I'm going down 2 and to the right 3. So my slope is negative 2 over 3 because the line is going down. For the next one, again, I'm going to pick a point here and here, and that's going up 1 to the right 4. So my slope is 1 over 4. Next, I have a horizontal line. The slope of a horizontal line is 0, and that's because I'm not rising at all, but I'm running however many units I need to run. And finally, we have a vertical line, and the slope is undefined because I can rise, but I'm not running to the right or left at all. So that means I'm trying to divide by 0, which I can't. So what we just found here, our slope, is also known as the average rate of change if you were to put some units into the scenario. And I just put a little reminder here for you for what the formula of slope is. Here's your grade 9 version. Here's the fancy function notation version. So instead of y2, f at x2. So that's the y coordinate when you sub in x2 minus f at x1. So the y coordinate when you sub in x1. So let's take a look at average rate of change. Like I said, average rate of change is just slope. So we're going to start off by determining the average rate of change if you're given a graph. So Megan crushes, not just hits, a baseball. Its path is modeled by the graph below. So she starts at time 0, she hits the ball, it flies up, then gravity brings it back down after 6 seconds. And it says determine the average rate of change between 1 and 3 seconds. So at 1 second, the height is 10, and at 3 seconds, the height is 18. So now, doing my slope, okay, and I'll just write a rock average rate of change. Either one would be fine. My y2 is 18 minus my y1 is 10 over x2 is 3 minus x1 is 1. And now that is 8 over 2, which is 4. And my units, it was height on top, so meters, and time on the bottom, so seconds. 4 meters per second. Let's do the next one. Between 2 and 4 seconds. At 2 seconds, the height is 16, and at 4 seconds, it's also 16. So my average rate of change is 16 minus 16 over 4 minus 2. That's 0 meters per second. Now clearly, there was motion going up and then coming back down, but between those seconds, between 2 and 4, because we're at the same height, on average, it looks like it didn't move at all. Next, the average rate of change between 1 and 6 seconds. So at 1 second, we're at 10, and at 6, we're at 0. So our average rate of change is 0 minus 10 over 6 minus 1. So y2 minus y1 over x2 minus x1. It's like I'm creating a line segment here, and that's what my average rate of change is. And as you see, that line is going down, so I'm expecting a negative rate of change. And that's going to be negative 10 over 5, which is negative 2 meters per second. And the negative just tells you that from 1 to 6, there is an overall downward trend from start to finish. And just going back, let me draw in the other lines that you found the slope of. So between 1 and 3 seconds, this is what you found. You can see that this line is steeper. It's also a positive line. And then the other one was horizontal, hence our rate of change that was 0. What about when an equation comes into play? So a rock is tossed upwards from a cliff that is 120 meters above the water. The height of the rock in meters above the water is modeled by h at t equals negative 5t squared plus 10t plus 120, where t is the time in seconds. Determine the average rate of change between the interval 0 and 1. Okay, so I want to find out what h at 0 is and what h at 1 is. And I like to organize my work by doing those calculations on the side and then doing my rate of change. So at time 0, it's just the y-intercept, which is 120. At time 1, if I replace my t's with 1, so negative 5 times 1 squared plus 10 times 1 plus 120, that's going to give you 125 meters. And now I'm ready for my average rate of change. So 125 minus 120 over 1 minus 0. Now you'll notice I did this coordinate minus this coordinate. You could have done the other way around as long as you stayed consistent. So if you did 120 minus 125 over 0 minus 1, it would still work out. But here we get 5 over 1, so that's 5 meters per second. Let's try from 2 to 3 seconds. So we need h at 2 and we need h at 3. So h at 2, when you plug 2 into both of those t's, punch it into your calculator or do mental BEDMAS math, we get 120 meters. When you plug in 3, so negative 5 times 3 squared plus 10 times 3 plus 120, we get 105. And now we can do our average rate of change. So 105 minus 120 over 3 minus 2, that's negative 15 meters per second. So that means there's some downward movement at this point. And finally, the average rate of change between 0 and 4 seconds. H at 0 is that y-intercept of 120. H at 4, so negative 5 times 4 squared plus 10 times 4 plus 120, and that gives you 80. And now our average rate of change is 80 minus 120 over 4 minus 0. That's negative 40 over 4, which is negative 10 meters per second. So average rate of change, nothing new. It is just grade 9 slope where you're doing y2 minus y1, x2 minus x1. Sometimes from a graph, so you can read your coordinates from there, or sometimes you have to find them by plugging into an equation. Next, we have the instantaneous rate of change. The instantaneous rate of change, or the IROC, corresponds to the slope of a tangent. Now, what is a tangent? A tangent is a line that touches a graph at only one point, and when you draw that tangent line, it goes in the same direction as your relation. So here I have some sort of maybe cubic function, and here's my point, and this dotted red line is the tangent. It's just a line, and when it passes through this point, it's going in its direction at that moment in time. Now, sometimes your tangent line will hit the function at another point. That's fine, but the focus is on the point of tangency here. Okay, now how do you find this instantaneous rate of change? Well, you can do it graphically. So if you have a graph of your function, you can sketch your tangent and then estimate the slope using y2 minus y1, x2 minus x1. Find a point on that tangent and do your slope. Now, this isn't going to be the most accurate way to find the instantaneous rate of change, but it can give you an estimate. The other way is to pick 2 points that are really, really close to the point that you're looking for, and then find the slope using that. And we'll talk about that in one of the examples, and I'll show you what I mean by 2 points that are really, really close together to get an estimate of your instantaneous rate of change. So we're going to start with a graphical example though, and I have a function here, and we're going to sketch the tangent at x equals -3, and then we're going to estimate. So here we are, and I want to try to be kind of going in the direction, so maybe something like this. It looks like I'm about to switch directions, so I'm not really going to be horizontal. I'm kind of halfway. So I'm going to estimate this as my tangent line. And if I look at this tangent line, I have this coordinate here, of course, so -3, 5. And maybe this point roughly is -1, 8. And then I can just do my slope. So my instantaneous rate of change is 8 minus 5 over -1 minus -3. And that's going to be 3 over 2, or 1.5. So there we go. At x equals 3, the instantaneous rate of change is approximately 1.5. Now, if you don't draw your tangent line very well, then this method isn't ideal because it's not going to be very accurate. So here's method 2. Determine the instantaneous rate of change of f at x equals -x squared plus 6x at x equals 5. So I'm just going to plot the point, but I'm not actually going to use my graph. Here it is. I do expect my tangent line to be a negative, to have a negative slope, so maybe something like this. Very rough. But I'm going to show you the algebraic way. So I want to pick a point to the right and to the left of x equals 5, something super, super close. And what I'm going to do is I'm going to add 0.01 and I'm going to subtract 0.01 to 5. And those are going to be the 2 points that I use. So first, I'm going to evaluate f at 5.01. So I'm going to do -5.01 squared plus 6 times 5.01. And I get 4.9599. I'm going to do the same thing with 4.99. That's me subtracting 0.01 from 5. And when I do the same thing, so -4.99 squared plus 6 times 4.99, I get 5.0399. So it is very close to 5 because the coordinate is at 5, 5. And you'll see these points are extremely close. They're 0.02 units apart, so barely apart. They're almost touching. So at least this way, though, I do technically have 2 coordinates, even though they're pretty much on top of each other. But now I can do my slope formula. So instantaneous rate of change is equal to 4.9599 minus 5.0399 all over 5.01 minus 4.99. And when I punch that into my calculator carefully, so remember sometimes you might have to put brackets like this in your calculator when you do your division to ensure BEDMAS is followed, but you get -4. So if you actually look at my sketch of the tangent, my tangent line looks more like a slope of -3. So not the most accurate using the graphing method. This is, I would say, a lot better. And when you get to calculus, you'll get to an even better method. Now that you have the slope of the tangent at x equals 5, determine the equation of the tangent line at this point. Well, this is just pure grade 9. Y equals mx plus b. M is your slope, b is your y-intercept. We have our slope of the tangent line. because that's what your instantaneous rate of change is. Now, I just need to plug in my coordinate, which I can read off my graph. It's 5, 5, and solve or isolate for b. So this is 5 equals negative 20 plus b. Bring that negative 20 over, and the y-intercept is 25. So here is the equation of your tangent line. All right, last little example. I made it a word problem for us. Draco Malfoy's Averte Statum spell hits Harry Potter and he flies through the air. Harry's height in meters can be represented by the function h at t equals negative 0.1 t squared plus 0.6 t plus 1.1, where t represents the time in seconds. Determine the instantaneous rate of change at 2 seconds. Okay, so my test values that I'm going to be using are going to be 2.01 and 1.99. So add 0.01, subtract 0.01. And when I put 2.01 in for both t's into this function and punch it into my calculator, I get 1.90199. You're going to notice I'm not rounding anything, or else that will mess up my accuracy. And I do recommend, pause the video, make sure you punch it into your calculator properly and that you get the same thing as I do. And then we'll do the same thing for 1.99. Punch it in, both t's, watch your exponents and your brackets, and we get 1.89799. Now I'm ready for my instantaneous rate of change. 1.90199 subtract 1.89799 all over 2.01 minus 1.99. And we punch that in, and I get 0.2 meters per second. And because it's a word problem, I will write a therefore statement. Therefore, the instantaneous rate of change at 2 seconds is 0.2 meters per second. And there we go. So, average rate of change, you're just doing slope, like in grade 9. Instantaneous rate of change, you're still using the same slope formula. However, you're finding the slope of the tangent line. And that's the slope of the line at one specific point on your function. But we can create 2 helper points so that we can use our slope formula. And that's it for your rate of change.